is often that you will not have enough data points about certain phenomena, but you can make a good judgment about the probability distribution, and hence you can generate additional data based on the probability distribution, and that would help you to build a good model. So, I mean, if your judgment about probability distribution is correct and your model gives you good results, then obviously you have you are moving in the right direction. So, role of probability and statistics in machine learning. So there are several reasons probability and statistics are important in machine learning. So it's not only from the perspective of data, its analysis, data generation, but also from the other side where we are developing algorithms. So from both perspectives, probability and statistics are important. So probability statistics help decide what kind of analysis is required on the data if you need statistics or a learning algorithm. Okay, some algorithms are derived from statistics. So for example, softmax is a multinomial distribution. Naive Bayes is based off Bayesian statistics. So some a lot of algorithms are explained and justified with the help of probability and statistics. Some algorithms are totally based on that. So we have maximum likelihood classification, Bayes classification, and so on. Some experts view all of machine learning as some form of probabilistic approach. So that's another key perspective. So all algorithms that we have developed so far, they can be explained and implemented in a probabilistic way. So everything else is a functional estimation assumptions and numerical fitting techniques. ठीक है, so वो कहते हैं कि यार एल्गोरिदम्स जो कोर एल्गोरिदम है, कोर अप्रोच है, वो प्रोबेबिलिस्टिक है, ठीक है ना, बाकी जो है वो आपकी सिर्फ फिटिंग है या फंक्शनल एस्टिमेशन है. So this is, our background into why we need to study probability and statistics. I hope you guys are now convinced about it. So let's review the basic elements of probability. So here we study uncertainty, sample space, event space, probability measure, and so on. So uncertainty. So we need to study uncertainty because our measurements are noisy. So we may not be making accurate measurements. Our data sets are limited in size, and there are a lot more data out there. So we are not sure how the data might be varying. There is ambiguity. Often in real world data, so the word bank can mean a financial institution. So bank can be a financial institution, the side of a river, tilting an airplane, etc. So there are multiple meanings associated with real world phenomena, and it applies to numbers as well. So numbers might be interpreted in many different ways. Which meaning was intended based on the word that appear nearby. So we might, want to deal with that uncertainty by looking at, surrounding words, and that's a statistical investigation on its own. A limited model complexity. So our model might, the real world phenomena might be very complex, whereas our model might be very simple, and it might not be able to deal with all the different scenarios which are possible in the real world. And that means that there's a lot of uncertainty in the results, in the predictions that are being produced. So we have to understand that there is going to be uncertainty in our measurements, in our results being produced, in the data that we are feeding into our models, and all that uncertainty has needs to be taken into account while building any models. So probability theory provides a consistent framework for quantification and manipulation of uncertainty. So to deal with that uncertainty, we have to go into probability and look at various concepts, various tools, various techniques for dealing with the uncertainty. Probability theory also allows us to make optimal predictions given all the information available to us, even though that information may be incomplete or ambiguous. So that's another key advantage of probability theory and its concepts, that given that we have incomplete information, we have ambiguous information, it has some theorems or some tools that would help you make predictions with incomplete data. Okay, so a key concept, the next key concept that we should learn is sample space. So when we go and apply probability on any problem, so sample space is the first key concept that we should be aware of. Sample space, which is denoted by capital omega, is the set of possible outcomes of an experiment. Okay? So you carry out an experiment, or you are dealing with a situation, so you collect, all the results of that experiment as omega. Point W and omega are called sample outcomes, realizations, or elements. So within that sample space omega, there are many points W, which you can call sample outcomes, realizations, or elements. So now we understand what sample space is. So let's look at that a bit further. So there is another concept which is called events. So subsets of omega are called events. So you conducted an experiment. For example, if we toss a coin twice, then omega is equal to head, 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 tail, tail, head, tail, tail. So this is your sample space omega. Now you define different events. So one of the possible events that you might define is that the first toss is heads. So that event has 2 points which are HH and HT. We say that event A1 and event A2 are disjoint, mutually exclusive, if their intersection is an empty set. So first flip-flop being heads and first flip-flop being tail is an example of events which are disjoint events. So we have added a few key concepts to our toolkit. So how do we measure probability? So probability measure or probability is, we will assign a real number, probability of A, to every event A, called the probability of A. Okay. So now that we have sample space and we have events, for every event, we want a numeric measurement, which is your probability. So to qualify as a probability, P must satisfy 3 axioms. So axiom 1 is probability of A is greater or equal to 0 for every event A. So probability has to be positive, should always be positive. Probability of sample space is equal to 1. So if you sum up all probabilities, then the probability of the whole sample space is going to be 1. Axiom 3 is, if A1, A2 are disjoint, then you can take the union of all those events, and their probability will be equal to sum of all the events. So these are the 3 events which basically any probability P must satisfy. So now we understand that, okay, what is sample space, what are events, and what is probability. So here is a good recap of elements of probability. So to understand probability, you need to understand sample space omega. You need to understand an event, which is a subset of omega. There is an event space F. Then obviously you need. So probability measure is, the properties, axioms that probability measure has to satisfy is, probability has to be positive. The sum of all events in the sample space is equal to 1. And, if A1, A2 are disjoint, then, the probability of AI is equal to, of all the events is equal to sum of the probability. So for disjoint events, you can basically sum up their probabilities. So let's move further and look at basic properties, which include conditional probability, multiplication law, law of total probability, Bayes rule, independence, joint probability. So these are the few key properties that we will further look into. So joint probability, so it's, in real world, obviously you have multiple events and you are interested in their joint probability. So probability of X and Y. So you would write it as probability of X comma Y. So, and then you have conditional probability, which is probability of X given Y. And you can see that, how we have written that down. So that means, that if event Y has occurred and we want to find the probability of event X, then we can write it as probability of X given Y. So let's look at joint probability. So joint probability is a statistical measure that calculates the likelihood of two events occurring together and at the same point in time. Okay, the events are X and Y, and you are interested in finding out what is the probability or likelihood of these events, occurring together. So joint probability is probability of event Y occurring at the same time that event X occurs. So it's a simple concept where we are looking at multiple events occurring together. Okay. The following formula represents the probability of event intersection, probability of X intersection Y, where X comma Y, two different events that intersect. So obviously, you have two different events, and they might, in some areas they might be occurring independently of each other, but they might be occurring together in certain areas. So probability of X and Y, or probability of XY is equal to the joint probability of X and Y. So here is an example. So we are looking at a deck of 52 cards, and we are interested in joint probability of picking up a card that is both red and 6. Okay, so probability of 6. So 6 might occur in other colors as well. So 6 intersection red. So there are 2 cards out of 52 that are 6 as well as red. So the probability is 1/26. So that basically represents the intersection. So there is a diamond and there is a heart out there, that are basically red as well as 6. So there are basically 2 sets here, one with 6, but obviously the card having 6 are of 2 different colors. 2 of those cards are, red. So we have, the intersection area where they are basically the 2 sets are joining. Basically, 2 sample spaces are joining. Okay. So you can also use, the following formula for the joint probability. What you can do is, probability of 6 intersection probability. Red is equal to probability of 6 multiplied with probability of red. So probability of 6 is obviously 4 out of 52, and probability of red is 26 out of 52. So basically, you have 1 out of 26, which is the final probability, which is the joint probability of 6 and red. So that was joint probability. So in many cases, as we saw with cards, we are interested essentially in the joint probability of events. In other cases, we might be looking at independent and conditional probabilities, which are additional concepts. So assuming that probability of P is greater than 0, the conditional probability of A given B. So we are interested in probability of A conditional to, some other event B. So probability of A given B is equal to probability of AB divided by probability of B, and probability of AB basically is equal to probability of A given B into probability of B, which can also be written as probability of B given A into probability of A. So that's basically conditional probability according to product rule. So assuming that, the events A and B are independent, they don't depend on each other. So that means probability of AB is equal to probability of A multiplied with probability of B. So in this case, joint is equal to product of marginals. Okay. So we might have another interesting case in which, 2 events A and B are conditionally independent, given some other event C, if they are independent after conditioning on C. Okay. So probability of AB given C is equal to, in that case, probability of B given C into probability of A given C. So because, they are conditionally independent, what we can do is this will be then equal to probability of B given C into probability of A given C. So वो आपका product rule जो है वो उस पे apply हो गया है, ठीक है. So let's look at an example on how we might be applying that on a useful scenario. So we have a scenario where 60% of machine learning students pass the final exam and 45% of ML students pass both final and midterm exam. So that's our problem statement, giving us the background. What we are interested in this problem is what percent of students who pass the final also pass the midterm. So this is the problem statement that we have got. We can reword it as, what percent of students pass the midterm given they pass the final. So, this is conditional probability. So probability, we are interested in probability of midterm given final. So we know that, 60% of the students have passed the final exam. And we know that 45% of the students have passed the both midterm and final exam. But we don't know how many students, pass the midterm exam given that we know that 60% of the students have passed, of those students have passed the final exam. So probability of midterm given final will be equal to giant probability of midterm and final divided by probability of final. So that because we know the giant probability, which is equal to 0.45, and we know probability of final, which is 0.60. So that gives us the conditional probability that 75% of the students basically also pass the midterm who actually pass the final. So that this kind of problems can often be encountered in our business domain, where we have to basically make a judgment based on certain events that have already occurred, and we are interested in finding out, or predicting certain outcomes. So conditional probability and independence. So let P be any event such that its probability is not equal to 0, which means that it is going to occur. Then probability of A given B is equal to probability of A intersection B divided by probability of B. A is independent of B if and only if probability of A intersection B, the both events occurring is equal to probability of A into probability of B. So they are independent. If they are independent, A and B, if we know for sure that they are independent, then their giant probability will be equal to probability of A into probability of B. So that means that we can rewrite our formula as probability of A intersection B is equal to probability of A into probability of B divided by probability of B, which means that conditional probability of A given B is equal to probability of A. So that's a useful result that you can often get and use if we know about two real world phenomena in your domain, and if they are totally independent, then you can get this kind of result. You can use that. So let's move on. So we have now covered a few basics like what is probability measure, what is conditional probability, what is giant probability, what are implications of independence on calculation of conditional probability of events, and so on. So obviously, in real world, in our sample space, we have multiple events, and they might have some relationship, some overlap, they might be totally independent, and we can verify that, and accordingly we can calculate the probabilities and use those results for making our predictions. So Bayes rules is an important tool in our arsenal that can help us deal with a lot of probabilistic scenarios. So Bayes rules basically uses a few key concepts like prior probabilities, posterior probabilities, and then we develop Bayes rules on that. Obviously, we use our knowledge of basic concepts like giant probability and independence and all. So prior probability, okay. So Bayes rule works in certain mindset, okay. So these concepts, prior probability, posterior probability, are basically explaining that mindset. So prior probability in Bayesian statistical inference is the probability of an event before new data is collected. So you have to understand this, okay. You already have certain data, and based on that data, you have certain probability. So that probability will be your prior probability. So this is the best rational assessment of probability of an outcome based on current knowledge before an experiment is performed. So you have basically a continuous changing situation. So at certain point in time, you collected certain data, and based on that data, you have your assessment of probability. That is your current knowledge. So based on that current knowledge, you have your prior probability. So prior probability of an event will be revised as new data or information becomes available. So, we have certain prior probabilities about certain things. So let's say after a week's time or after 2 weeks' time, we have collected more data and we have processed it. We have developed understanding around it. The data is clean and uh, we are confident about our data. So we add that data to our existing data set. So accordingly, your prior probability of that thing would change. So let's say, you are studying cancer or you're studying coronavirus or you're studying fraud. So as you go on and collect more data about a fraud category, your prior probability is going to change accordingly. So a counterpart of prior probability is posterior probability. ठीक है? So prior probability is based on your current knowledge. ठीक है? जितना आपके पास डेटा उस पर आपने probability calculate की वो आपकी उस event की prior probability बन गई. A posterior probability in Bayesian statistics is the revised or updated probability of an event occurring after taking into account new information. ठीक है? So once you add new information, that probability is posterior probability. So posterior probability is calculated by updating prior probability using Bayes theorem. So posterior probability आपके Bayes theorem से आ रही है, ठीक है? In statistical term, the posterior probability is the probability of event occurring given that event B has occurred. ठीक है ना? So इवेंट बी पे आपने डेटा कलेक्ट किया, ठीक है ना, और फिर आपने उसकी इवेंट ए की प्रोबेबिलिटी कैलकुलेट की, ठीक है. सो इवेंट ए की प्रोबेबिलिटी बेसिकली बेस्ड ऑन आवर नॉलेज ऑफ इवेंट बी, ठीक है ना. इवेंट बी का नॉलेज हमारे पास था जो हमने डेटा से कैलकुलेट किया हुआ था, ठीक है. इवेंट ए को हमने जज करना था कि इवेंट ए की क्या प्रोबेबिलिटी है, ठीक है. So event A की probability will be your posterior probability. So let's look at conditional probability. The conditional probability of an event B is the probability that event will occur given the knowledge that event A has already occurred. Okay, so that's another key term that is associated with. Sometimes we use just the term conditional probability. We don't refer to it as a posterior probability. So this probability is written probability of B given A. So posterior probability is essentially your conditional probability. So probability of B given A is the notation for that we use for conditional probability. So let's dive further into conditional probability. So in case where event A and B are independent, so now we understand that what independent events are. So I won't explain it further. The conditional probability of B given A is simply the probability of B that is P of B. So just a few minutes ago, I explained that if two events are, totally independent, then, probability of A given B will be equal to probability of A is equal to probability of B. Okay, A given B is equal to probability of A. Or if you are looking at probability of B given A, then that will be equal to probability of B. So if events A and B are not independent, then probability of intersection of A and B is defined by. So, we want to look at the joint probability of A and B. Then that will be equal to probability of A into probability of B given A. So these are basically, overlapping events. Okay? So in that case, we will have this formula. So we will, then use this concept of conditional probability to develop our Bayes. So let's look at an example of a conditional probability to understand it better. So in a card game, suppose a player needs to draw 2 cards of the same suit in order to win. Of the 52 cards, there are 13 cards in each set. Suppose first player draws a heart. Now the player wishes to draw a second heart. Since one heart has already been drawn, so that is known, that is one event. There are 12 hearts remaining in the deck of 51. So conditional probability, probability of, second heart that you can draw, given that, first heart has already been drawn, is 12 out of 15. Okay. So here we have another example, another scenario. So in this scenario, we are supposing that an individual applying to a college determines that he has 80% chance of being accepted. So that's one scenario. And he knows that dormitory housing will only be available for 60% of the accepted students. So, the hostel facility will be available to only 60%. So he has 80% chances of being accepted, and those who are accepted, they have only 60% chance of getting enrolled in hostel. So the chance of the student being accepted and receiving dormitory housing is defined by probability of accepted and dormitory housing. So this is the giant probability that he is interested in. So he wants to be, what he is interested in, his chances of getting accepted as well as, getting the hostel facility as well. So that will be equal to, according to the rules of conditional probability, it will be equal to probability of dormitory housing given accepted into probability of accepted. And, you can multiply the conditional probability to get the final answer, which is 0.48. Okay. So you can see the Bayes rule, so Bayes rule basically gives you the conditional probability of event A given B. The formula calculates the posterior probability of A occurring given that B has occurred. So in Bayes rule, we are interested in, we have certain information of event B, and we are, which is our prior probability, and we are interested in calculating probability of event A, which is our posterior probability. So A and B are events. B, we know the probability of B, and we know that it is greater than 0, it is positive, the event has occurred. We know that probability of B given A is the probability of B occurring given that that A is true. So we have this knowledge. Probability of A and probability of B are probability of A occurring and probability of B occurring independently of each other. The posterior probability is thus the resulting distribution, probability of A given B. So probability of A given B is equal to probability of AB, which is the giant probability, divided by probability of B. This is according to conditional probability. Then according to product rule, we can further write it as probability of B given A into probability of A divided by probability of B. And additionally applying the law of total probability, we know that, we can write probability of B as summation of, probability of B given A into probability of A. So that basically gives you the Bayes rule under various situations. So let's look at an example. So essentially in real world scenarios, we need Bayes rule because, we have the conditional probabilities. In real world scenarios, there is conditional probabilities that exist and that can help us derive or determine the final outcome. So suppose you have tested positive for a disease, suppose not you, but someone has tested positive for a disease. What is the probability that you actually have the disease? Okay, so we are interested in that. You conducted some test and that test came out positive. Now, is there 100% chance that you have that disease? You have fever and you check that you with the help of a thermometer. So you know that no, you have a test that shows that you have a fever. Now, having a fever does not mean that you have coronavirus. You know, um, so then you can basically look at the conditional probabilities to determine that someone having a fever, what are the chances that they have the coronavirus and so on. So it depends on accuracy and sensitivity of the test and on the background prior probability of the disease. Okay, so probability of test given disease. So test is positive and the person has the disease. So let's say that probability is 0.95. Okay, so that if the test is if that is the case, then having the positive test means that there is 95% chance that you have the disease. So it's a really accurate test. There is another scenario as well. The test is positive, but you don't have the disease. So there are 5% chances of that as well. So that is false positive. So test is basically giving you a false positive about somebody having the disease. The probability of the disease itself is like 10%, and that is the probability that we have calculated after doing a lot of tests. Okay, now we are interested in posterior probability. So we are interested in probability of disease given the test. So the doctor basically has to determine that, okay, if somebody's test is positive, then what are the chances that they actually have the disease? So this is the important question that your doctor has to answer. So we use because we are interested in posterior probability, so we use the Bayes rule. So if we apply the Bayes rule on this situation, then we know that probability of disease given test is equal to probability of test given disease into the probability of disease itself divided by the probability of test being positive. So probability of test given disease, that is like 95%. That is probability referred to as sensitivity as well. So probability of disease is, that is our prior knowledge about the disease is like 10%. Sorry, 0.01 is 1%. Divided by probability of test, which is around 10%. So that gives us basically around 8% chance that we have the disease. Okay, let's look at law of total probability. Law of total probability says that probability of test is equal to probability of test given disease into probability of disease. So, if we apply that, then we get 0.1085. Okay. So now we know the Bayes rule, where it might be applied, what are the key concepts behind Bayes rules, how conditional probabilities and various rules related to that help us develop the Bayes rule, and how you might be able to verify that, and we know the basic properties of probabilities that we might use. There are some other concepts, that help us deal with probabilistic behaviors, events, and situations. So these are random variables and probability distributions. So let's look at a few key concepts such as random variables, probability mass functions, probability density functions, expected value, Gaussian distribution. So these are the key concepts that are used in development of algorithms, that are used in verification of our results, determining the confidence that we have in various predictions that we are doing. So let's first look at random variable. So primarily, the first thing that we are interested in is how do we link sample spaces and events to the data. Okay, so we can develop, we can get a sample space, so we can collect some data, and that that data is some part of the real world possibilities. We might have in real world, we might have billions and billions of transactions. Out of those, maybe we get 10,000 transactions, and how can we link them? That's what we are interested in. How can we link our sample space with the real world events? So to do that, we have a random variable, which is basically a mapping that assigns a real number x of omega to each outcome omega. Okay, so basically a random variable is a mapping essentially that is giving you a number for each event omega. So for example, you flip a coin 10 times, let x omega be the number of heads in the sequence of omega. So if omega is equal to this sample space, h, th, and so on. So these are all the possible events that you have. Then x of omega, if omega represents the number of heads, is basically 6 out of all the 10 out of our sample space that we have got. Okay, so when looking at random variables, there are two types of random variables. So we have discrete random variables and we have continuous random variables. So in real world, sometimes we have situations where we can take random variables as integer numbers, as integers 1, 2, 3, 4. So they are discrete. So can only take a countable number of values. For example, number of heads are always going to be 1, 2, 3, 4, 5, 6. They cannot be like 1.1, 1.2. So there are not infinite number of possibilities for number of heads. So they have to be discrete numbers. Distribution defined by so their distribution, if you have discrete random variables, then their distribution is defined by probability of mass function. So if you take all the discrete random variables and you look at their probabilities collectively, which is their distribution, then you would see, you would be basically using a probability mass function. Okay? Then obviously in real world, we don't always have discrete phenomena. We may have a continuous phenomena. So sometimes we can measure random variables as real numbers. So for example, you might be interested in time taken to accomplish a task. So that might be like 1.1 hours, 1.2 hours, up to 2 hours. So you have a range, but within that range, it can be any number. It can be 1.25 and anything like that. So you don't have discrete quantity representation. You have basically a continuous real number representation for the real number for the random variable. So in that case, if you take all those possibilities together, then their distribution is defined by probability density function, which is PDF. So along with random variables, we have added two new concepts, which are probability mass functions and probability density functions. So we have for discrete random variables, we have probability mass functions, and for continuous random variables, we have probability density function. So probability mass function, let's look at it in a bit more detail. So if x is a discrete random variable, which represents our probabilities, then its range R of x is a countable set. Okay, because it is discrete, so we can list the elements in Rx. In other words, we can write Rx is equal to some discrete numbers, x1, x2, x3, and so on. So note that here x1, x2, x3 are possible values of random variable x. Random variables are usually denoted by capital letters. So that's the notation that we are using. To represent the numbers in the range, we usually use lowercase letters such as small x or x1, y, and small z, etc. So the notation associated is explained. Okay, so let's look at probability mass function example. So let's toss a fair coin to ice, and let x be defined as the number of heads that is observed. Okay, so find the range of x or x as well as its probability mass function, which is referred to as p of x. So our sample space is given by head, tail, tail, head, and tail. So if you toss a fair coin, then a pair of fair coins, then these are the possibilities that you would get in your sample space: head, tail, tail, head, and tail. Both of them can be tail as well. So the event that we are interested in, let x be defined as number of heads. So those possibilities can be that number of heads can be 0, number of heads can be 1, or number of heads can be 2. So basically the range of x, a random variable x, or R of x can be defined as 0, 1, and 2. So probability of x for some k can be, probability of x is equal to k for k, k can be 0, k can be 1, k can be 2. So you are going to see either no heads, either 1 head, or 2 heads. So probability of x, given x is 0, you see no heads, which is your event probability of TT, that is 1 out of 4. Probability of x is 1. So we have 2 events for that, HT and TH. So that gives us 1 by 2. We are basically summing those probabilities because they are independent. Probability of S given 2, which is only 1 event that can occur. So that is probability of HH, which is equal to 1 by 4. So this is how we can calculate probability mass function for any event that we might be interested in for discrete random variables. So many times we are interested in, plotting probability mass functions as histograms. So here we have some scores and their relative frequencies. So probability of scores being in the range of 20 to 30, 70 to 80, 80 to 90, 90 to 100. So we have their frequencies as a histogram. So often we basically plot probability mass function as histogram. We can also represent them or illustrate the probability mass function, visualize it as a table as well as a histogram. So then basically if we have some random variable x, and for that we have 5 discrete states like 0, 1, 2, 4, and we have here probabilities. So that is with the help of probability mass function, you can get the probability of x given any of its values. So the other counterpart is probability density function, which is another tool that we can use to measure probability in a real world scenario. So probability density function can be used in a scenario where we have a probability distribution for a continuous random variable as compared to a discrete random variable. So that would help you determine probability for a real world scenario where your measurement is a random variable that is a real number and that is continuous. So when the probability density function is graphically portrayed, the area under the curve will indicate the interval in which the variable will fall. So that will give you basically the range. The total area in this interval of the graph equals the probability of continuous random variable occurring. Probability density function. So probability density function basically is measured in an interval. Okay. So because there is no single point at which you can measure the probability for a continuous random variable. Probability density function is not to be confused with probability mass function, which is applicable for discrete random variables. So these are two different things. So if a random variable is discrete, then you can measure probability with probability mass function. But if it is continuous, then you are going to use probability density function. So this is how we might be measuring probability density function. As you can see in the figure, we have certain colored area which gives us a range where we basically can check the probability. So what is the probability that a person will weigh between 150 pounds and 250 pounds? So that's the question that we have related to probability density function. So we can write that as probability of y in this range, like greater than 150 and less than 250. To answer the question, the shade area on the graph. If you are doing it graphically, that's how you do that. Then approximate the area from looking at the shaded area. It is about 75%. So we look at the total graph and we see that if the probability is in that range, we are covering 75% of the area, and that gives us the probability for y, given that y is in the range of 150 to 250. So that's how we measure the probability if the our random variable, our real world phenomena has continuous or real world or real number representation. So probability density function versus probability mass function. To illustrate the probability that today's temperature will be 80 degrees and 80 degrees exactly. So if you are doing measurement like that, then you have discrete measurements, and you can apply probability mass function. The probability that temperature will be between 80 and 85 degrees is measured by probability density function. But if you are looking at ranges, if you want some exact value, like, today the temperature is going to be 30.50 or 30 degrees centigrade. So that's an exact value, and you have discrete probability measurement in the form of probability mass function. But if you have a continuous measurement, if you think that, okay, you can measure probability in a better way, you can get a better sense of probability of temperature. If you say, on the temperature, what is the probability of, temperature being 35 to 40 degrees centigrade, then obviously you are going to use probability density function. The probability density function basically calculates the probability of a range of outcomes. And you have, an intuition that how you are going to calculate that. Okay, so in the later case, the temperature could be 8101, 81,001, and so on. So you are going to take all those values by essentially coloring the area that falls in that range, and comparing that to the overall area being covered by the distribution itself. So if you are dealing with PDF, then in PDF the probability of a single outcome is always 0. Okay, because you can't measure it. Okay, so this is because a single outcome is represented by a line which has no area under the curve. So we are essentially using area under the curve to measure PDF, and line has no area, so we can't really measure it. However, for continuous random variables such as temperature ranges in the example that we studied, PDF can be used to calculate the probability that today's temperature will be between 80 and 85 degrees centigrade, whatever. Okay. So now we understand how we are going to use probability density functions. Okay. Let's look at independence. So two random variables X and Y are independent. Now we are basically looking at real world probabilities of real world phenomena as random variables. Okay. So probability of X, Y, if they are, if X and Y are independent, then that is equal to multiplication of their probabilities. So we have, probability of X given some value of X into probability of Y given some value of Y. Probability of Y given X is equal to probability of Y. For continuous random variables, probability of X, Y is often referred to as f of X, Y for some, events X and Y. So spin a spinner numbered 1 to 7 and toss a coin. Okay, what is the probability of getting an odd number on the spinner and a tail on the coin? Okay, so these are independent events. Probability of X, Y obviously is equal to probability of X into probability of Y. So probability of getting a tail on the coin is 1 by 2. Probability of getting an odd number, so 1, 3, 5, and 7 is 4 out of 7. So you multiply these two and you get the joint probability of X, Y. So now we are basically looking at the same probabilities, but obviously we are looking at joint probability, but we are looking at it as random variables. while looking at X and Y as random variables, not just events. Okay. So another key concept that we often use is expected value. So expected value is an anticipated value for a given investment at some point in future. Okay. In statistical probability analysis, the expected value is calculated by multiplying each of the possible outcomes by the likelihood each outcome will occur and summing all of those values. Okay, so we calculate expected value by multiplying each of the possible outcomes that will occur. Okay. By calculating expected values, investors can choose the scenario most likely to give them their desired outcome. Okay. So let's look at expected value example. To calculate the EV for a single discrete random variable, you must multiply the value of the variable by the probability of that value occurring. So take for example on normal six-sided die. Once you roll the die, it has an outcome equal to 1/6. Chance of landing 1, 2, 3, 4, 5. The expected value will be the calculation is straightforward. So 1/6. 1 has the probability 1/6. You multiply it. 2 has the probability 1/6. 3 has the probability 1/6. So the expected value is 3.5. So that basically tells you, if you roll a die an infinite number of time and you take the average, the expected value is equal to 3.5. Okay. So there are some statistics associated with probability distribution. So mean is equal to E of X. Mean is our expected value. Mean is often taken as expected value, and this is also equal to the first moment, or referred to as first moment, and that is equal to integral of x into f of x d of x, and for continuous random variable. So essentially we are integrating over the whole area. And for discrete variables, we are basically multiplying the probability of each event, each value with its probability and summing those up. So we can calculate variance, which is another important statistics. It is giving us the spread of value. So for any random variable x, its variance is equal to x minus mean whole square, E of x minus mu whole square, and then you can basically expand it. Then you can calculate nth moment as from integral from minus infinity to infinity x minus c raised to the power n. So variance is basically raised to the power 2, and nth moment is x minus c raised to the power n into f of x dx. So let's look at the Gaussian distribution, which is also referred to as normal distribution. So that's another tool that we use for for calculating probability of an event. Okay, so widely used to model distribution of continuous variable. In case of a single variable x, the Gaussian distribution can be written as n of x given mean and variance is equal to sigma square is equal to 1/2 pi sigma square root exp e raised to the power of this whole thing. So essentially what it is telling you that you can get probability of some event x given it is a continuous event then we only need to know the mean and variance, and we can calculate the probability. So if you can assume the mean and variance for some real world phenomena, then you can get the probability of some x because of this bell-shaped curve. So normal distribution basically is associated with it is with the assumption that this real world phenomena has this bell-shaped curve. So if it has normal distribution, then we can calculate the probability with the help of this formula. Okay. So often we have different classes having different means and slightly different variances in certain domains. So maybe you have different classes of fraud, or maybe you have different species of something, and for some feature x, which is your random variable that you are measuring. So maybe we are measuring length of something, and the range of measurements that we may have is from -5 to 5. So it can be any value in that range. So given that we have the behavior of that that phenomena is that you have two different means for four different classes, and you have slightly different variances for those classes. So so that gives you basically a good understanding of what your data distribution is, and how it is varying, and you can use this understanding for calculating the probability of any probability of x. So for d-dimensional, so obviously in real world you don't have a single measurement. So you might have 10 different measurements for a real world phenomena. So you might have length, you might have weight, you might have weight. For a transaction, you might have 10 different features. So in that case, obviously, you cannot deal with a simple Gaussian distribution. So you have essentially a multivariate or multi-dimensional Gaussian distribution. So for a d-dimensional vector x, so vector x has these d dimensions. Each of those dimensions is an independent feature. The multivariate Gaussian distribution then takes the form of n of x given mu and this covariance matrix summation. So summation symbol basically represents a d cross d covariance matrix, and we also have determinant of this covariance matrix denoted by bars with the summation symbol. So this is a formula for multivariate Gaussian distribution, which again we use if we can have given our data set. So given our sample space that we have selected, and if we can assume, or if we have measured that our sample space has Gaussian distribution, it follows, each of those features follows the bell-shaped curve, then we can use this formula to calculate the probability of x. So for this case, we can calculate the covariance matrix given some random variable x and y as x minus mu of x integral over s2 and s1, y minus mu of x into f of xy, which is the probability of X and Y, the giant probability of X and Y. And in a simplified form, we can write it as it is जो convention है उसकी E of xi minus mu I into xj minus mu j. So xi is some feature, xj is some other feature, and for each for all possible values of those features, we have a mean of that feature class that we are subtracting it from, and then the summation by multiplying these, we get the these two vectors essentially, we get their summation matrix, covariance matrix. So these are a few key ideas from probability and statistics that we basically use to develop the tools that we need for our analysis and for our prediction, and to develop the intuition that we need for developing our algorithms. So many of our algorithms basically work on assumption that we have a normal distribution or Gaussian distribution in our data, and there is some statistical independence as well, and so on. So I hope all these concepts would help you understand and apply your knowledge of various machine learning techniques in a more informed way. So do we have any questions, any thoughts on the topics that we have covered so far? Hello.
जी डॉक्टर साहब.
Ji, this is finished from my side. Do you have any questions?
No, Dr. Saab.
No, Dr.
So would you be able to, revise all this and do a few simple exercises on your own? So we have a Kaggle notebook associated with this lecture, with most of these concepts, if not all of these concepts. So do go through that. Hopefully that will help you apply some of these concepts on the data sets that you have got. Maybe you can look at the probability distributions. You can look at phenomena with independent, they are not independent, and so on. Thank you for your time. Can you mark your attendance in the thread for batch 3? Okay, thank you very much. Allah Hafiz.
Allah Hafiz. Allah Hafiz.
Hafiz.